we must understand that just as there is gravitational potential energy by virtue of an object's position in a gravitational field, there is also electrical potential energy by virtue of an object's position in an electric field, and charged particles can flow and generate current just like water in a river can flow and generate its own kind of current. Oppositely charged particles, because of their charge, have the potential to accelerate towards each other, just like an object on the edge of a cliff has the potential to accelerate towards the Earth because of its mass. And in each case, it is the field that does the work to produce the acceleration. As charged particles move within an electric field, their electrical potential energy changes. For a uniform field, the magnitude of this change is equal to the opposite of the object's charge times the electric field strength times its displacement from the reference point in the direction of the field. This leads to the concept of potential difference, which is the difference in electric potential between 2 points in an electric field, expressed as the change in electrical potential energy over electrical charge. The SI unit for potential difference is the volt, which is equivalent to 1 joule per coulomb. This means that as a 1 coulomb charge moves through a potential difference of 1 volt, it gains 1 joule of energy. The potential difference for the two terminals of a common battery is anywhere from about 1.5 volts for small batteries to around 12 for a car battery. Batteries do work to move charges, so volts are not a measure of energy. They are a measure of change in energy per unit charge. As charge flows, it produces usable energy, like the way that flowing water can push a water wheel as it moves past. In this way, we can discuss electric current, and our ability to manipulate this current is responsible for our mastery of electrical power. A current exists whenever there is a net movement of electric charge through a medium. This can be defined as the total charge passing through a given area divided by the time interval. The SI unit for current is the ampere, which is equal to 1 coulomb of charge passing a particular cross-sectional area per second. The direction of the current is always opposite the movement of negative charges, but a current can be generated by particles of either charge. Most materials that are conductors of electricity are metals that allow for the free movement of electrons from atom to atom, or electrolytic solutions with charged ions in solution. The ability of a material to oppose the motion of charge is called resistance, which will be unique to a substance and vary by the dimensions of the material. This is the ratio of potential difference to current, measured in ohms, which are represented by the Greek letter omega. These are equal to 1 volt per ampere. Electric power, which is the rate at which charge carriers convert electrical potential energy to other forms of energy, is given by current times potential difference, which is measured in watts, or joules per second.
When we look at a simple electrical circuit with just a battery and a lamp, we know that to turn the lamp on, we need to connect both ends of the wires to the terminals of the battery. Once we connect these wires, the circuit is now complete and electrons can flow from the negative through the lamp and then back to the positive terminal. So for the circuit to be complete, we need a wire to carry the electrons from the power supply and over to the light. This wire is our hot wire. Then we need to connect another wire from the lamp and back to the battery for the electrons to get back to their power supply or from their source. Now this wire is our neutral wire. The hot wire carries the electricity from the power supply and it will take this over to the load. The neutral wire carries the used electricity back to the power supply. If we look at a residential electrical system in North America, then we will find 2 hot wires, a neutral wire, and some ground wire. So we're going to replace the battery with a transformer, and there we go, we have a complete circuit. The electricity in this circuit is AC alternating current, which is different from the DC direct current which we saw with the battery. With DC, the electrons flow directly from A to B in only one direction, much like the flow of water down a river. But in our homes, we have AC alternating current, which means the electrons alternate their direction between forwards and backwards, much like the tide of the sea. Now in North America, we have a split phase supply to most residential properties. So we have the 2 hot wires and 1 neutral wire. We simply have 2 120 volt coils which are connected together in the transformer. The neutral is then connected to the center between the 2 coils. When we connect our multimeter between a hot and the neutral, then we're going to get a reading of around 120 volts. And we get the same reading for the other one. That's because we're only using half of the coil in the transformer. But then when we connect between the 2 hots, we get 240 volts because we're using the full length of the transformer coil. Now, if we have a load on only one half of the coil, and the load is for example 20 amps, then the hot wire will carry 20 amps to the load, and the neutral wire will carry 20 amps back to the source. We can measure the current in a cable using a current clamp meter. Now, if we have another load on our other half of the coil, and the load is a different value, say for example just 15 amps, then the neutral will only carry the difference between these 2 values back to the transformer or back to the electrical source. So in this case, one side we have 20 amps and the other side we have 15 amps. So the difference between these is 5 amps. So the neutral will carry 5 amps. Where does the rest of this go? Well, it will pass through the 2 hot wires. Now this is what we have in most cases because there are multiple circuits with different loads in the residential property. However, if we had a load on both coils and they are of equal value, say for example 15 amps each, then there will be no current flowing in the neutral wire. So where's it going? Well, it's flowing back and forth on the 2 hot wires between the load and the source. That's because it's AC alternating current and the transformer is center tapped with a neutral. So while one half is moving forwards, the other half is moving backwards, and the current will flow into the other circuit instead of back via the neutral. Okay, so the hot wires carry the electrical current from the supply and over to the load, and the neutral wires carry the electrical current from the load and back to the supply. So what does the ground wire do? The ground wire, under normal operating conditions, will not carry any electrical current. This wire will only carry electrical current in the event of a ground fault. Hopefully, this wire will otherwise never ever be used at all in its entire life. It's just there for an emergency path for the electricity to get back to the power source instead of it passing through you. The ground wire in most cases is a bare copper wire. It's uninsulated, but in some cases it is covered with a green insulation. This wire has a very low resistance, so electricity will prefer to travel along it because it's easier and can get back quicker. Now if we go back to the simple circuit with a battery and a lamp, if we now run another wire, we run this from the positive terminal over to the lamp and we connect this to the metal of the lamp holder, then this is effectively our ground wire. As you can see, it's not being used to carry electricity. If the hot wire touches the metal casing, then the electricity will now flow through the ground wire instead. If the hot wire is connected to both the neutral and the ground, then it will now flow through both wires back to the source. But as the ground wire has less resistance, then more current will flow through it. When electricity finds a way to leave its circuit and return to the source through a different way than its neutral wire, this is called a ground fault. Coming back to the house, the electricity flows through the hot wire and into the light and then back through the neutral. But if the hot touches the metal casing, then it will instead flow through the ground wire, back to the panel, through the bus bar, and then back to the transformer via the neutral wire. The ground wire has a very low resistance, so it causes a huge and instantaneous increase in current, which will trip the breaker. We therefore connect the ground wires to anything that could potentially become a potential path for electricity to leave its circuit, such as the metal pipes, the metal plates on the light switches and the outlets of their boxes. We also need to run one to the outlets because often our appliances are made of metal or they're covered with a metal casing, things like washing machines and microwaves. When you look at a receptacle and plug, you'll see that there is a hot terminal, a neutral terminal, and a ground terminal. The casing of something like a washing machine is connected to a ground wire in the lead, which goes to the plug, through the receptacle, and back to the panel to save you from an electric shock. Now, let's say you're outside with no shoes on and the ground or the soil is moist. If you touch a hot wire, you could complete the circuit and the current may pass through you to get back to the supply. In this case, the resistance is going to be very high, so the current might not be high enough to automatically flip the breaker and cut the power. This will likely lead to the person's death. Luckily, we have the GFCI receptacle or the GFCI breaker. GFCI stands for Ground Fault Circuit Interrupter. We're going to look at a circuit breaker version, but essentially they're going to work the same. This GFCI breaker is going to be connected to both the hot and the neutral of the circuit, so we can monitor the wires and ensure that the current running in the hot wire of the circuit is equal to the current running in the neutral wire of the circuit. If the current is not equal in these two wires, then it is clearly flowing back to the source via another route. We then have a ground fault. The breaker will realize this and very quickly and automatically flip to cut the power and kill the circuit. Connected to the main panel, we will find a thick copper wire which leads out to a ground rod. The ground rod is buried into the ground outside near the property.